Hello, my name is Nikolaj, and in this talk I want to present our paper, PPP-Completeness and Extremal Combinatorics. And this is a joint work with Romain Bourneuf, Lukáš Folwarczný, Pavel Hubáček, and Alon Rosen. So let's start by talking about Ramsey's theorem. So in Ramsey's theorem, it says that if you have an edge coloring of the complete graph on 2 to the n vertices, and you use two colors to color in each of the edges, then you will have a monochromatic clique that has a size of at least n over 2. So Ramsey's theorem guarantees that a certain substructure, namely this monochromatic clique, exists if the collection of objects, namely the vertices, is sufficiently large. A similar sort of theorem is known as the Erdős-Rado Theorem, and it says that if you have a family of n sets whose cardinality is greater than n to the power n times n factorial, then you will have an n sunflower of size n plus 1. And recall that a sunflower is a collection of sets that all pairwise intersect in the same set that we call the kernel. And then each of the sets, they sort of have petals because they have unique elements that are not in this kernel. And I sort of tried to illustrate that with this, with these circles that I put on this slide. So both of these, so what is sort of in common with, what do these two theorems have in common? So they're both examples of extremal combinatorics. So extremal combinatorics studies collections of objects and the relation between the size of the collection and emergence of a certain substructure. And so if this collection of objects is sufficiently large, such that the theorems guarantee that the substructure exists, then this induces a total search problem. And in particular, if the substructure can be efficiently verified, it induces a total search problem that's in TFNP. So the problem that we ask in this work is what is the complexity of total search problems that are induced by extremal combinatorics. And note that both Ramsey and the sunflower problem, the problems that are induced by the theorems, are going to be easy to solve if you're sort of given the collections explicitly. So in order to make the problem non-trivial, what we do is we consider an implicit representation of the collections instead. So for the case of Ramsey, what we have is we have a circuit that computes the edge coloring of the graph. So you can give this circuit an index of two separate vertices, and then you will get back the color of the edge between these two vertices. So the implicit Ramsey problem is given a circuit that computes this edge coloring, finds an output, a monochromatic clique that has a size of n over 2. This is going to be a set of indices into this collection. And note that this can indeed be verified efficiently, so it does belong to TFNP. Similarly for sunflower, what we do is we have a circuit that's where you give it an index into the collection, and then it outputs a representation of the ith. So if you give the input I, it's going to give a representation of the ith element as a characteristic vector. And then you're asked to find an n sunflower of size n plus 1. And this can also be efficiently verified. And so Krajicek and Komagotsky, Naur, and Yogev show that Ramsey and sunflower are PWPP hard. And for Ramsey, it uses something called the graph hash product that I'll sort of that I'll go through now because we'll be needing it later in this talk. So in the graph hash product, what we do is we basically want to use an oracle that solves the Ramsey problem to find collisions in a hash function. So and this first thing is just a fact. So there are randomized constructions of a graph on 2 to the n over 4 vertices that do not contain a monochromatic clique of size n over 2. So suppose we have one of these graphs, and we have a hash function that shrinks. It takes in n bits and outputs n over 4 bits. So if we consider then we also have this other graph where what we do is we take the we color if you have two vertices. The color between these two vertices is going to be determined by hashing each of the vertices and then taking the color from the smaller graph. And sort of the interesting thing here is that we know that the smaller graph does not have a clique, and in particular, this larger graph is exactly large enough such that the Ramsey's theorem applies. So we know that it must have a clique, and in particular, this clique must have been introduced by the collisions in the hash function. So if the Ramsey solver gives us back a monochromatic clique, we can use that to find a collision in the hash function. And this is sort of the approach that's used to show PWPP hardness of Ramsey and Sunflower. So what we do in this work is that we characterize PWPP and PPP via extremal combinatorics. So we show that PWPP is captured by weak theorems in extremal combinatorics, of which Ramsey and Sunflower are arguably the case, while PPP is captured by strong theorems. And I'll go into more detail with exactly what this means, but essentially a strong theorem, you will have a tight bound on the size of the collection, while for weak theorems you will not. And so we show that PWPP and PPP are captured by these two different notions of extremal combinatorics theorems. And then we also significantly increase the number of complete problems for both of these classes. Because both of these classes were, like, unlike PPA or PLS, they were not known to have as many natural complete problems. And we sort of significantly expand on this set of problems. And at a high level, what we're doing is we're using efficient encodings that sort of translate these substructures that we're looking for into collisions in a circuit, such that we can use the pigeon solver. So other complete problems that were known for PPP are Blitzfeld's theorem, which was shown by Sotiraki, Sampetakis, and Siedelis, who also showed completeness for the related constrained SIS problem, which is related to cryptography. Then Hubáček and Vaclavec showed that a version of the discrete logarithm problem is also known to be complete for PPP. Also in concurrent work, Pasaka, Yannakakis, and Papadimitriou show that a version of the Erdős-Ko-Rado Theorem is also complete for PPP. And note that this is essentially, so I will be showing basically a version of this result, but note that their statement of the Erdős-Ko-Rado theorem is significantly different than ours, and I'll expand upon that when we actually get to the definition of the problem. So let's define these classes that we're going to be working with. So the classes are defined by their canonical problems. So let's start with the first one, which is the weak pigeon. So in weak pigeon, you're given some shrinking circuit and asked to find a collision. So since the circuit is shrinking, by the pigeonhole principle, there must be a collision somehow. So if you have n pigeons and you put them in n over 2 pigeonholes, there must be 2 pigeons in the same hole. And note that this is what I mean with a weak theorem, because clearly if there are n pigeons in n over 2 pigeonholes, either like many of the holes will contain 2 pigeons, or one of the holes will contain a lot of pigeons. So the condition that we have 2 pigeons in the same hole is sort of not a very strong condition that we get from this other thing. So this is the weak pigeon, and PWPP is defined as the set of all problems that are reducible in polynomial time to weak pigeon. Then similarly, we have the pigeon. And here we have a circuit that's not shrinking. So it takes in n bits and also outputs n bits. And here we're asked either to give a pre-image of 0 or to find a collision. And here we sort of use what we call a strong property of the pigeonhole principle. Because if we have n pigeons and we have n pigeonholes, then either all of the pigeonholes have a pigeon, in which case C is essentially a permutation, or there must be 2 pigeons in the same hole. So this is a stronger version of the same theorem, and this again defines the class PPP, and we sort of show that this notion of so for the pigeon, what we have is we have this tight bound, namely in pigeons and in pigeonholes, and then we know that if the condition, namely collision, that we're looking for is not satisfied, some other property must be satisfied, and then we can use that namely that it's a permutation, and then we can use that to define a total search problem. Okay, so the result that I'll be going through now is to show that this Erdős-Ko-Rado theorem is indeed complete for PWPP. So what we do is we take a family of sets, and then we say that this family of sets is an intersecting family if no two sets from the family are disjoint. So all of the sets sort of intersect somehow. And Erdős-Ko and Rado in 1961 showed that if you have, they sort of gave conditions, they gave bounds on the sizes of these intersecting families. And their bounds were like significantly more general than what I'm presenting to you here. But we also do present significantly more general versions of this Erdős-Ko-Rado problem, but sort of in the interest of keeping the presentation short and simple, we choose this special case. So if you have a universe of size 2n, so some set of size 2n, and then you consider subsets of this set of size n, so any intersecting family of n sets must have a size of at most 2n minus 1, choose n minus 1. And essentially how this bound comes about is, suppose we take these 2n elements and then we fix one of the elements. So let's say we choose the first element, and then we say that all of the sets in the intersecting family has to contain this particular element. And then we consider the remaining 2n minus 1 elements from the universe, then we have to choose n minus 1 of these. And there are 2n minus 1 choose n minus 1 ways to do this. And this is how the bound is obtained. And note that this means that if we have more than 2n minus 1 choose n minus 1, family of if we have a family of insets of size larger than this bound, then there must be two sets that are in fact disjoint, and this induces the total search problem. So we're going to define a problem that we call weak Erdős-Ko-Rado, where essentially like the sunflower thing, the circuit is going to encode this collection of objects. So you're going to give it an index of the ith set, and then it's going to return to you the characteristic vector of the ith set. So it's basically a bitmap where the ones indicate which element from the universe are contained within the ith set. And here we we guarantee that this circuit is larger than the bound by saying that its input size is alpha, which we define as log 2n minus 1 choose n minus 1 rounded up plus 1. So this guarantees that we have more sets than we need. And then we say that a solution, what we want to say is that if we have, like, for an arbitrary circuit, we will have this Erdős-Ko-Rado theorem, this Erdős-Ko-Rado condition hold, and there must be two disjoint sets. But the way we choose this representation, it's not guaranteed that a particular index actually represents an n-set. So I might say that the first set is empty set, or it contains all the elements in the universe. And we sort of, because this is wrong, this doesn't conform to the conditions required by the Erdős-Ko-Rado theorem, so we say that this is also a solution. We allow evidence of the fact that the encoding is wrong to also be a solution. And similarly, if we have two indices that encode the same set, this is a collision, and this would also mean that the Erdős-Ko-Rado condition does not apply, so this is also allowed to be a solution. And finally, we have the actual condition that we're, like the actual case that we're interested in, namely that if all of the indices are in fact distinct and they are all n-sets, then the Erdős-Ko-Rado theorem applies, and then we have to find two disjoint sets. So what we show is that this weak EKR thing is PWPP hard. So yes, what we're going to do is we're essentially going to be using cover encodings. So we want to map like these different, like these three conditions. We sort of want to map back and forth between collisions and these things. So what we're going to use is these cover encodings. And cover encodings allow us to encode, so we have a universe of some fixed size n, and we are only interested in k-sets of this universe. Then we can use cover encodings to sort of optimally encode this. So basically we take all the k-sets and then we order them lexicographically. And this is our encoding. So if you want to encode a given set, you give me 2n bits as input, and then I'll give you the index into this lexicographical ordering of this particular set. And then the decoding function obviously does the opposite. Note that these functions can in fact be made efficient, and also the functions, like if I give it an input, so we're going to be using this with n sets of a universe of size 2n. But if I give this cover encoding function something that does not have a Hamming weight of n, like the output is going to be meaningless. It's not going to correspond to the actual set, but it's still going to be well defined. And in fact, it will be arbitrary. So if we give the cover encoding something that's not an n set, the output can be whatever. And this turns out to be important, and I'll get back to that in a bit. Okay, so the first thing we want to do is we want to establish PWPP hardness. So this means that we are given some shrinking circuit, C prime, and by the Merkel-Damgard construction, we can sort of, like, exactly how much it shrinks doesn't really matter that much. So let's just assume that for simplicity that this circuit shrinks by 2 bits. So we have some circuit that takes in alpha bits, and then it outputs alpha minus 2 bits. This is our weak pigeon instance that we want to find collisions in. So we're going to build an instance of Erdős-Ko-Rado as follows. So we're going to take these alpha minus 2 bits, and then we're going to prepend 2 zeros to it. And then we're going to put it through the cover decoding function. And basically, when we prepend these 2 zeros, because we use the lexicographical ordering, we know that the result is not going to contain 1. So whatever set, so we give this cover decoding function the index of some set, and then it gives us back the set. And we know that the cover decoding function has to give us something that does not contain 1, and also by correctness it has to give us something that's actually an n-set. Like that's just correctness of the decoding function. And this means that sort of by correctness of this decoding function, all the outputs are guaranteed to be overlapping n-sets. And this means that all the solutions that are left are going to be the collisions. And these collisions allow us to find collisions in the original pigeon instance. Because this covered decoding function is injective. So this is basically how we establish hardness. In order to establish, so one thing that's interesting about our work here is that unlike other classes of TFNP, like PLS or PPA, there's a natural algorithm that sort of solves the problem. And this means that oftentimes inclusion results are going to be fairly easy to show, whereas the hardness results might be hard. While in our case, it actually seems to be the opposite. Like variants of this graph hash product seem to work in a lot of different cases, but what was the most challenging part was actually showing inclusion. So I'll also be showing inclusion now for this week, Erdős-Ko-Rado Theorem. So, okay, so this should be, so the C, the topmost C is correct, the other one should be C prime. So we use C prime to denote the weak pigeon instance and C to denote the EKR instance. And so we have some instance of a EKR, and it's going to give us, so we give it an index, and it's going to give us back the corresponding set. And this is going to be the C. And then we're going to get back some bitmap, some representation of this n set. And then what we're going to do is we're going to case depending on whether or not this set contains 1. So if it does contain 1, we're going to flip all the bits. And if it does not contain 1, we're going to leave it be. We call this to normalize the vector, for lack of a better term. And this essentially means that the set we're going to get will always start with a 0. And then we're going to take this set and we're going to put it through the cover encoding function. And then we're going to get back the index of this particular set. And we know that because all of these sets do not contain 1, that the cover, like the encoding that we get for any of these sets is always going to start with a 0. So the first bit is always going to be a 0. So we're just going to get rid of this bit. And then we're going to keep these remaining alpha minus 1 bits. And note that this is indeed an instance of a weak pigeon, because we have a circuit that shrinks by 1 bit. And essentially, so what we want to argue now is that we can basically find any of the solutions that we have to the EKR thing. So if we don't have something that's actually an n set, like I said, this encoding function would just like arbitrarily map it into one of the other sets, which creates a collision because the cover encoding function is injective. So yes, and another thing, if we have a collision, like if this EKR thing have two sets that correspond to the same thing, then again by injectivity of this cover encoding and this normalization, this will also produce a collision in the weak pigeon instance that we create. And finally, if we have two disjoint sets, since we're working with n sets over a universe of size 2n, the only disjoint sets are going to be like a set and then the complement of that set. And here, like the normalization process is going to map both of these into the same representative because we're going to take the complement. And this so this maps a solution of the third type from EKR into collision, which allows us to use the weak pigeon solver to find it. And so note that EKR is a strong theorem. So this bound is tight. So if we do have an intersecting family, then like this is the largest possible you can get, and it's a tight bound. And in addition, the largest intersecting family has to contain either n, like the, so let's say the elements of the universe are the numbers 1 to 2n. It either has to contain the set 1 to n, or it has to contain the complement from n plus 1 to 2n. And we can use this to create a strong version of the EKR theorem. So we define a problem called the Erdős-Ko-Rado problem, which again, so now we have now we want to ensure that the collection has the precise number of elements that we need. So we have this alpha bits as input, and then we're going to keep the first three types of solutions, and then we're going to add a new type of solution. So if the collection is indeed maximal without containing any disjoint sets, then it either has to it has to contain one of these two sets. So we allow this as a solution. So if we have the largest possible collection of items, So basically, we will either have either one of these two sets have to have a pre-image, or we have to have two disjoint sets if this collection is encoded correctly. And sort of to guarantee that we have the correct size of the circuit of the collection, what we do is we sort of artificially add this a bound on these values x and y. So they have to be strictly less than the bound. And what we show in the paper is that the Erdős-Ko-Rado theorem is in fact PPP hard, or it's PPP complete. Sorry, it says hard here, but it's actually PPP complete, the Erdős-Ko-Rado theorem. And we also show this for a significantly more general version of the Erdős-Ko-Rado theorem. We also consider other problems from extremal combinatorics. So we consider the following problems. So by Sperner on antichains, Cayley on spanning trees, and these other problems. So we consider the implicit total search problems that are induced by all of these problems, and then we show some various bounds. So the bounds that we show are the following. So the Erdős-Ko-Rado, Sperner antichain, and the Cayley on spanning trees has the property that their weak versions are PWPP complete, while their strong versions are PPP complete. And for Mansell and Turan and Szabo, it's a bit more complicated in the sense that we were not able to show as strong bounds as we were for the other problems, and it's sort of unclear the extent. This Turan problem defines a hierarchy basically. So if you'll note here, we have this in the definition of the Turan thing. We have this parameter R. So it basically creates a hierarchy of these problems, and it's sort of unknown whether or not like where it fits exactly in relation to PWPP and PPP. So to summarize, what we do is we give a new take on PPP and PWPP in terms of weak and strong theorems from extremal combinatorics. So our work suggests that maybe the reason showing inclusion for Ramsey and Sunflower has been difficult is due to the lack of type bounds, especially in relation to PPP. So thank you very much for your attention.